The objective of this video is to differentiate between 4-bit encoding and variable length encoding. Sounds really technical, but I think it's a fun lesson, a very fun lesson. So we'll take what you know about binary values right now and connect it to the different compression techniques that exist. Remember, some of these lessons, if they ever feel short, that's so you have plenty of creativity time. Once you get on Tinkercad, the website, you're going to have probably more than what you know what to do with in terms of resources. So with that in mind, what we have not started is adding binary numbers. Pretty easy, but haven't even looked at doing any math with binary yet. In progress is just wrapping your mind around compression. Completed is the definition of compression, taking something of a lot of bits, make it into fewer bits. So speaking of which, let's do a little review first here. What is the mass storage medium you're writing to? That is the question that you should ask when thinking about compression. So hard disk drives, they have a low random access speed and moderate sequential read speed. So fragmentation matters a lot. So when I say random access, and if you hear about RAM, random access memory, the random access, like there's nothing actually random about anything that a computer does. Even a random number generator is still very much not random. But let's focus. So random access means you can access a piece of information in the middle of the drive. You don't necessarily have to go in order. So it may look like the drive head is jumping around randomly, but it's definitely not. It's just going to the right place for the right data that you've requested. My think right here on this page is, does compression matter if you can randomly access any part of the storage device you need? And why or why not? If we're talking about a storage medium like USB flash drives, well, they have a low to moderate read speed and usually a slightly lower random access speed. So fragmentation doesn't really matter here, but for large data sets, the overall read time can make a noticeable difference. So think right here, what type of data do you think would work best on a USB? To answer this, you might want to talk about what kind of data would not be good for a USB. SSDs have high read speeds and almost as high random access speeds. Fragmentation doesn't matter here at all, except in a very few cases. And what I'm saying here is, remember that in this unit we'll want to be mindful of the difference between processing and storage. We just spent 3 slides talking about storage. And all of this vocabulary and all these discussions should help lead you to better understanding of hardware and the understanding of what we're using the hardware for in class. Remember, lossy data or lousy data compression, this is the converse of lossless data compression. So on these storage devices, we're compressing things for the sake of creating more room for other things. In these compression schemes, dropping non-essential data from the data source can save lots of storage space. For example, the human eye is more sensitive to subtle variations in luminance than it is in the variation in color. So because our eyes cannot detect variations in color that well, creating a compression algorithm to help us save pictures is a really great idea, and we will not notice the difference. JPEG image compression works in part by rounding off non-essential bits of information, and there is a corresponding trade-off between preserving information and reducing its size. I always think it's funny in those like crime shows when they say like zoom in more and more of a video that was recorded or a picture that was taken. There's a complete limit to that. You just can't have a computer magically create something that's not there to zoom in on. Okay, so after talking about data storage and the way in which we can store things through the compression, let's really dig into the details of how these things are being stored in the first place. So think right here on this page, what is the difference between the two just using the table alone for reference? You have your letters here, and you have a 4-bit encoding for the letter, and then you have a variable length encoding. Simply staring at this chart, go ahead and write out your thoughts. What's the difference? All right, so now narrow your view onto the letter. It's A, I, H, W. Okay, why would this ordering be here? This is not alphabetical ordering, right? In the 4-bit encoding, the order doesn't matter. All of the encoding is a 4-bit value. Okay, and don't get confused about the word encoding. Just think of it as like a naming system. So this 4-bit encoding, 000 is the name of the letter A. When the computer gets 000, it will show the letter A on your screen. That's all an encoding is, a naming system. So if I'm looking at variable length here, it's 2 zeros, and then 1 0, and then it's growing, right? So here's why. The ordering is being created because of the word Hawaii. So if I'm trying to find a way to save the word Hawaii in the smallest way possible, this encoding is the way I'd go, the variable encoding. H would be 0 1 0, A would be 0 0, W would be 1 1 0, A, I already said A, 0 0. And then the two I's would be 1 0. So think about this. Why was it encoded in this way? At the end of the day, how many bits does it take total to represent Hawaii? I'm counting down here 1 1 1. So there's 3 4 5 6 7 8 9 10 11 12 13 14. This is a 14-bit value. The key to variable length compression is in the computer's ability to identify the most commonly used data. So in our Hawaii example, A occurred twice. I occurred twice. So in this example, we only need 14 bits instead of 24, giving us a compression ratio of 1.7. So you have to be able to detect patterns to have a successful compression. And the great thing about variable length encoding is it's a lossless way of compressing files. The question is, what would happen if you used a variable length and then lossy to compress a file? And just relax, don't take this question too seriously. I just want you to make a little prediction here. Predicting is good for the brain, and obviously it's challenging. So make your quick prediction here. And now let's think about another question. Why is the lossy technique okay for music and image files? A few slides ago, I explained why it's good for image files. Our eyes cannot detect variations in color, so we don't need to encode different types of color that the eye can't see in the first place. So why is the lossy technique okay for music and image files? It says here many of the compression schemes in widespread use today, including MP3, JPEG, these are lossy techniques. These permit significantly greater compression ratios that would otherwise be possible. So using lossy for JPEG is great. It is possible to achieve compression ratios of 10 to 1, 20 to 1 or more with this, depending on how much loss of detail we are willing to tolerate, okay? This compares with the values of 1.5 and 1.7 in the earlier described lossless schemes. Using these lossy compression schemes, that 192 million bit high resolution image mentioned could be reduced to only 10 or 20 million bits. So that is a very significant number. 192 million down to only 20 million, that's pretty good. Data compression schemes are an essential component in allowing us to represent multimedia information like in a concise and manageable way. I want you to now put that all in a greater context here for your DOL. Okay, don't forget there's an IB question. Choose one of the 7, especially on a lesson like today. I'm sure you may have been frustrated. I hope you utilize Google. I hope you utilize myself and other students in the class to help you. But okay, just choose one of these IB questions, and then for the DOL, we're just creating a table like this.